Okay, a theorem Marcinkiewicz. So let R is between 1 and infinity, t from L1 Rn plus LR Rn to M of Rn is a sublinear operator. Okay, if t is of weak type, 1 1 and weak type RR, then T is of strong type PP for any P in 1R. Okay, so it's important. It's an interpolation theorem. Using the T sublinear, we will have a T defined for P between 1 and R. Okay, so to prove this, first we consider when R is equal to infinity, and recall that L star, the norm star, infinity was equal to the normal norm infinity. So if we change the operator t by the operator norm of t to the minus 1 divided by t, okay, then one can assume that the norm infinity of t of f is less than equal than the norm of f. Okay, so we just obtain a constant equal to 1 with this change. Okay, so given f in L1 Rn plus Lr Rn, for each lambda positive, we define f lambda 1 x. This function will be f of x if absolute value of f is greater than lambda over 2, and 0 if absolute value of f is less than lambda over 2. Okay, and then we define f lambda 2 x equal to f of x minus what we just defined, f lambda 1 x. And so if we apply t to this, then we will have that the absolute value of t of f, it will be less than equal than t of f lambda 1 for x. Okay, this in particular this, and plus the norm, the absolute value of tf lambda 2. Okay, but that is going to be what is left of this function f lambda 1, and that can be bounded by lambda over 2. Okay, and we will also have that the set x, the point x that are in Rn, such that t of fx is greater than lambda, this set will be included to the set of the x in Rn, such that absolute value of t of f lambda 1 x is greater than lambda, okay, lambda over 2. So, okay, so these points, the elements of this set will be here, because here we are considering lambda over 2. Okay, so as t is a weak type 1 1, the set that we just defined, the absolute value, is less than equal than a constant lambda over 2 minus 1 multiplied by the norm 1. Okay, so the integral f1 lambda x dx, okay, and this will be equal to 2c lambda minus 1, okay, integral of f up to the value of f greater than lambda 2 of, again, the norm, the absolute value of f. So we just consider the definition of LP star, and we took the lambda over 2 and pass it to the side, and then we have the constant and the norm. Okay, so now we will use this to in this integral, that is the integral in Rn of t of f of x, absolute value p dx, okay. This because a property, the second property of the last video, we will have that is equal to p, the integral from 0 to infinity of lambda p minus 1, and then we have the set xrn t fx, okay, greater than lambda, okay, and we measure d lambda, and now yes, we will use this. It will be less than equal than p integral from 0 infinity lambda p minus 1, okay, and now this multiplied by 2c lambda minus 1 integral, okay, this estimate, lambda over 2 f x dx, okay, and now we will have the d lambda here because of the property, okay, and this will be equal to 2c p integral 0 infinity, okay. Now with this lambda we will have lambda p minus 2, and now again integral lambda over 2 fx, okay, this is lambda, okay, this is the lambda, okay, so this will be equal to 2cp, and now we will turn this to integral of Rn, but we will consider the integral of 2 absolute value of fx, okay, now we compensated lambda p minus 2 d lambda, okay, absolute value of fx dx, okay, so we will obtain 2cp, okay, and from here we will obtain 2f absolute value to p minus 1, and we will have this absolute value of f dx, okay, and here must be the integral has to be here, okay, Rn, so this will be equal to 2p cp p minus 1 and if norm of fp to the p, okay, this will give us the result for r equals to infinity, because we found the bound for t of f absolute value p, and now that depends of f of p, okay.